I'm going to zoom up a little bit from the talks we've been having so far, a little bit less in the details of how to make all this stuff work, and a little bit more about how we can conceptualize and think about maybe the network of the future. All right. This is a little slide. There's some things about me. It's my first time speaking at CHI-NOG, so thanks for having me here and letting me talk. I think anyone who tells you an expert is probably not, but I have thought about some of this stuff for quite a while. So we're in this together here. We're going to go through about 63 slides in the next less than 30 minutes. There's going to be time for questions, I promise, but I need all of you to kind of come with me on this. So we're going to start by a quick show of hands. Who in the room can raise their arm? All right, almost everyone. That's really solid. Good. All right, here we go. We're going to jump into this here. Really what I'm talking about today is network models, right? So we know what a network is, right? This is passing packets, forwarding frames, routers and switches, all of our favorite middle boxing that are strewn throughout, and connections, right? So that part's pretty easy. But what's a model? The first example here is a three-dimensional representation. That's not really what we're talking about right now, or a system or thing used as an example to follow or imitate. I think that's a little bit more accurate. Really what I'm talking about today is a conceptual model. So according to Wikipedia, a conceptual model is a set of concepts, which is not a very helpful definition. It's an abstraction of real things. That's maybe slightly more useful. A representation of a system. Now I think we're getting somewhere. It's used to help people know, understand, or simulate a subject. And that's really what we're talking about, right? So a network model to help us understand networks through this model. I think before we can talk about the new model, we probably need to review where we're at today or what the old model is. This is really kind of looking at things more from kind of the enterprise data center side of things than the ISP carrier side. But I think some of this applies to both. So this is the three-tier hierarchical network model, right? So I think everyone's probably fairly familiar with a diagram that looks something like this. In the campus network, you've got core aggregation access kind of spread throughout some IDFs and MDFs, just switches everywhere. The aggregation routers in the middle there doing some extra things, right? Interestingly, in this old model, the data center network looks fairly similar, except we've swapped a word out here. We've got distribution instead of aggregation. I don't actually know the reason that the campus and the data center models use different words there. I have kind of a guess here, right? So if we look at this in a client-server model, we've got client connections that are being aggregated into and across the network and then distributed back out to servers. Obviously, there's a return path there as well. And that starts to show us kind of the other three pieces of this model, which is your LAN, your WAN, and your data center. And I think it's worth pointing out that the reason we've kind of split this up into those three pieces is networks are complex, right? So this is a way for us to logically kind of break the network into pieces so we can actually wrap our minds around it and handle it. It's possible if we were able to simplify networks and network operations, we might not need those distinctions. And then also really this is actually kind of going like this. It's actually kind of a north-south traffic pattern, but at that point we're starting to get ahead of ourselves a little bit. So kind of backing off, the three tiers, right? What are they? So we've got core. This is really all about fast forwarding, right? We're just pushing packets. These core switches are really just gonna move packets. Then you've got this aggregation or distribution layer, and that's where all of the, I would say, kind of network services live, right? So this is your routing, your policy through firewall rules, or there's load balancing and things there. All of that stuff kind of goes on in that layer. And then access obviously is just kind of fanning out ports, right? Getting ports either to desktops or APs or into servers, right? Okay. So probably most of you by this point have heard of a leaf-spine network. It's a folded clause. So really what happened, I think, is server virtualization happened. And so we kind of started moving traffic patterns around from strictly north-south to more east-west, across the data center instead of just out of the data center. You can now turn stuff up and turn down. You can do vMotion and move things around. And maybe not as a direct relation to virtualization, but definitely kind of at the same time, we had massive, massive scale in data centers, which made us go back to a 1952 idea from a guy named Charles Kloss, where he basically figured out a way to do non-blocking circuit switching for telephony by using a bunch of crossbar switches and hooking them together in a certain way. There's actually like a mathematical formula that tells this. It's really kind of easier just to look at this leaf and spine and the way you can kind of scale it out, right? So show of hands, who's kind of at least knows what a leaf spine network is or has heard of this? Or okay, awesome, we're still in here. Good. Spoiler alert, that's not the two tiers that we're talking about today. So I think maybe, again, the reason to talk about a new model is maybe looking at the reasons why the old model is no longer sufficient, perhaps. So I think there's three problems with the three-tiered model, right? So one is this directionality, right? So it's really set up for north-south versus the new movement of east-west. And that's not just kind of north-south and east-west in kind of the data center itself, but I think outside of that too, right? As we start to see more and more kind of public cloud being part of your infrastructure, software as a service, those kind of things, there's a lot more movement, and the network kind of starts to look a little bit more ambiguous. And then also a big thing, if you can think of it directionally, right, so scaling up versus scaling out, which plays into the resiliency as well. If you need this resiliency and redundancy of these kind of big boxes at every level, it becomes pretty expensive. Also, spanning tree sucks. Blocking half your links is really no way to run a network. It just doesn't make any sense. And then kind of driving that home, I think the third real challenge here is it's very hardware-centric. So we're looking at these kind of monolithic, vertically integrated mainframe devices that we call switches and routers. This hardware layer, right, whether it's the aggregation or the distribution, is providing these services, but it's tied into that service being available on that box and having those boxes available. And then where you hook up your routers, your firewalls, your load balancers, all that stuff, right, you have these kind of hairpin physical connections. It's one of the reasons why network segmentation has been so hard to kind of get off the ground in a lot of places, because nobody wants to route all of their traffic back to a big firewall and then back out. It doesn't make much sense. You're doubling up the bandwidth on your network. And also this is potentially slow, right? So there's manual box-by-box configuration in the CLI. It's fairly slow. So we've created virtual chassis where you can kind of pretend that 2 routers are 1 or 2 switches are 1 to make it a little bit easier. But I think that's just pointing out the pain point rather than perhaps fixing it. And then again, this feature velocity, which kind of goes back to the reason hardware centricity is a problem. If you want to add features and things, you need to go through the hardware vendor itself or change the hardware out, right? Replacing TCAM is a pretty expensive operation. If you want to add more policy rules, if you want to add more firewall rules, if you want to add more MAC addresses or routing tables or whatever it is, that's all tied up in your hardware. Okay, so the way to kind of break away from hardware is with virtualization. I think just like we did so in the server space, you can also do this in the network space. All right, so the first piece to kind of think about here is network function virtualization. So we've got virtual network functions. So at this point, a network function becomes, right, that switch, that router, that firewall, whatever that function is itself, instead of being a device. Now it's a function. It can live in software. It can be in a VM or in a container, or sometimes even like built into the hypervisor. And these things can be moved around. We've also seen some really cool advancements in kind of the way servers work with NICs and pass packets. Back in the early noughties, I built a network that was based strictly on Linux bridging routers, and the PPS limits were terrible, right? We were never going to be able to build a 10 gig network with Linux routers at that point. Now with things like SRIOV and DPDK and FIDO and on, with both Microsoft and Linux, you can pass up to line rate 100 gig in an iMix situation on NICs, on servers. Pretty cool. So this stuff is actually a reality now. And then you can virtualize the network, right? So essentially what you're doing is you're overlaying a arbitrary topology on top of whatever physical network or logical network you have below it, right? So we can take this network, we can ignore the actual network and put in the connections we actually want and need independent of that network being there, right? And this is especially important when you start looking at that ECMP clause network where you've got connections everywhere, and now you can create the connections you want in an overlay. I think one thing to say about overlays, don't be scared of overlays. They're really not new at all, right? So we know about VLANs and MPLS and GRE, maybe even IPsec tunnels, SSL tunnels for your remote connections. All these things are overlays. But I think even more fundamentally than that, it's instructive to think about the fact that you've got a physical network, which is either wires or fiber optic cables. And then above that, you've got either a SONET layer or an Ethernet layer. And then above that, you've got an IP layer. And those are actually all overlays, right? You've actually already abstracted this network where the physical topology that might look like a ring or a mesh is actually being used in some different way with IP routing or switching even. You're creating these trees and routes. So this isn't something that's actually that new. Maybe VXLAN itself might be new, if that's the tunneling protocol of choice for your overlay. But there's lots of ways to do these overlays, and it's already happening. You're probably already doing it. So the new model, right? Which kind of what we came here to talk about. I think the first piece, as we're kind of teasing out the context of what this new model looks like, I would call switch inception. So if you look at folded class versus a multi-switch chip architecture, they're strikingly similar. And if you blow up a multi-switch architecture into an actual network and you've got devices, you potentially have more control and more visibility over that network. So just to kind of look at this in real time, right? So this is obviously a very well-architected leaf-spine network. And there's a multi-chip switch. Just in case you missed it, clause and multi-chip switch. So really this kind of looks the same, right? And if we dig into the clause network, I think as we start to move forward, right, so like Jericho 2 chipset is gonna do 10 terabits per second switch on a chip. So potentially, right, you can have super dense, like pizza box switches. You don't really need chassis probably anymore. And so then you can break out where you have a switch running a bunch of interfaces that just connect together in a mesh in a network. And so then you've got processors on that switch, which you can actually get a lot of telemetry out of, which you may not be able to do if you're embedding those chips into line cards, into under switches and things. So that's kind of your clause layer. And again, so basically what that becomes is now you've got this underlay physical network, which is essentially your core switch, right? So this is really, really good at forwarding frames, at passing packets, which means now you need like a services layer, or that access layer. If you're going to a controller-based SDN model, that looks a lot like a router, but just kind of blown up and bigger. So you've got the controller itself is your routing engine or your route processor or your supervisor or whatever you want to call it there. The virtual network functions themselves are like packet forwarding engines, so like your line cards. And then the tunnels that are the overlays become your virtual circuits. So again, it's really highly detailed diagrams here. You can look at the routing engine on the top. This is kind of how a router works. There's routing protocols that are feeding into the routing engine. The routing engine's then forwarding routes out into other routing protocols or different routing protocols. There's a routing table there. Communication between the PFEs or the line cards, which have a forwarding table. There's physical interfaces that are kind of your input and output to this, right? So that's kind of basically how a router looks. So if you look at an SDN-controlled network, kind of looks the same, except now you've got a controller at the top that's living on servers somewhere else. It's talking to both routing protocols as well as perhaps APIs and other things. It's got a routing table. It can push that down to virtualized network functions that are living wherever, perhaps on servers themselves. I mean, we all carry a supercomputer in our phone, in our pocket. There's laptops. Potentially you could push this all the way out to all of the edges, where you have these VNFs living completely at the edge, right? Kind of creating this new access layer where you can provide services. So we take lots of routers, and they're all still kind of there maybe, but really what we're doing is then pushing that router functionality through a virtualized network function into the edge devices, putting some controllers in there, and we're talking about kind of one big distributed switch that becomes your new access layer, right? This is kind of the new edge. So if you kind of view the network in these two layers, right? We've got this core switching layer that's your physical underlay, because that's what we need ASICs and ports to actually move packets. And then all of your services and policy and firewall rules and all of that stuff can happen in a software layer that's virtualized above that. You can now really start to think about things a little bit differently. So again, right, this underlay is a core switch, overlay as an access router. There's some characteristics that maybe kind of define this a little bit. This is kind of just a quick hits list. So the underlay, you probably want this non-blocking ECMP. You really want a nice IP fabric to move this stuff around. It needs to be resilient, high bandwidth, and it's made up of physical devices, because I don't know of any other way to move bits around yet. We may be able to do it without physical devices someday, but I wouldn't hold your breath. So then you've got an overlay, which is using tunnels. Those tunnels can be doing hashing stuff, right? VXLAN does some cool hashing so that you can take advantage of the ECMP, even though the underlay has a limited amount of routes. You can do policy-based routing, source-based routing, these things that we've been afraid to do for a long time, really complex policies and things, because the CPUs we had available to us on switches and routers just couldn't do it. If you move this to a server, you can do anything that you want. Maybe some of it's not recommended, but you can really get kind of wild and crazy with doing application-based routing and that kind of stuff, right? And these are all virtual devices. So again, this is kind of this two-tier network model, as I would visualize it, where you've got routing, policy, services, and security in software, and your connectivity in hardware. All right, so who cares? I think this helps a little bit, just as a conceptual model, really, because what you can do is you can focus on what matters. So if you split the network in this way, you can look at your physical core underlay network as a packet processing engine, right? As this thing that just needs to move packets fast and be resilient and be redundant, be rock solid. But it doesn't really worry about services or multi-tenancy or where the packets are actually going. It's just moving stuff around. So you kind of have this church and state divide now, where you can have your services that live in software and your connectivity that lives in hardware. How it helps in actual practice, right? If you actually kind of start deploying networks in this way, so scale becomes like a completely different issue, right? So if you're trying to push additional policies or access control list rules or MAC addresses or IPv6 addresses or IPv4 addresses into tables, those table sizes are now essentially infinite, because you can just throw as much computing power as you want at it, right? So it's not dependent on the physical underlay, because you've now moved a lot of that stuff out into this software layer. So your scale becomes exceptional. And then also updates, right? Because now you're running this in a very different way. You could potentially can don't have to touch this physical underlay. It's not providing services, so you probably don't have to update it very often. Just keep the security basic, and then all of the multi-tenancy and stuff can be in controlled failure domains inside of these overlays on top of the network, where you can do patching and do feature additions and things like that much quicker and much more easily. You can build a kind of this CI/CD pipeline and build into it and change your controller, and there's all kinds of neat things you can do when you're not dependent on software that's proprietary and built into a specific big expensive router or switch. So essentially the idea here, right, is if you extrapolate this out, you can build this universal network platform, right, for within your own domain, right? So it provides consistency because you've got this, again, in order to have these VNFs living out there as the PFEs on the edge devices, you essentially have this controller that's controlling all of that. And so you can push out the same policies everywhere. If you abstract that policy language, you can really use this very powerfully to provide consistent experience at all devices, at all edges. It makes it a lot simpler because, again, now you're kind of looking at the network as a single system where you can configure services and things like that as needed. And then potentially your visibility goes up as well. Instead of doing show commands on individual boxes, you can look at this controller, which is pulling in state from the entire network, and can show all of you that. And it unifies the domains, right? So, like I said, we're kind of already doing a lot of these overlays, right? So you've got remote workers who are SSL VPNing into something. You've got sites that are doing IPsec tunnels. You've got MPLS tunnels coming in. If you start to look at that as these overlays as a single, that's the actual corporate network, is this overlay network, and connect it together and configure it and control it in that way, I think you have some really interesting synergies, maybe. So use cases, like I said, this is already being used, I think, out in the wild. To steal a line from William Gibson, right? The future is here. It's just not evenly distributed. So some folks are probably like, yeah, man, I get this. It's okay, of course. Hopefully others, it's not so obvious. There are definitely a few service providers who have been built like in the last few years that are really like excellent case studies for exactly this way of doing networking. You can really kind of still have your dumb pipes that are really efficient and effective and robust and resilient, but run services over the top. And so you can still monetize your own network by looking at it this way, right? So things like SD-WAN, there's MSPs out there. There's a lot of folks that are kind of doing things with this or around this or like this already. And then, like I said, in the enterprise, I think you potentially have this network that now spans, instead of having to break up the logical domains, you can have a kind of multi-cloud, campus branch, remote office, single universal network platform to run your network on, which is especially cool if you're doing things like application development and containers across multiple clouds, and those need to be accessed by users who never show up at the office. Okay, well, how do you control the security on that at all? And how do you even network, build that WAN? Well, it's all overlays, and you just tie it all together. Right. So what if you don't want a controller? You're going to lose a lot of the benefits that I just talked about, but you can kind of do this right with BGP EVPN. It kind of acts as a control plane potentially. You're missing out on the management plane, so some of the policy stuff and all the other fun stuff you may not be able to do, but there is a way to do that. When we start talking about this and overlays, I think there's always one camp of people who are like, no, you want native SDN, right? Not overlays. You want open flow. You want these things to all work. The problem is that the underlays are already out there. There's this big network called the internet that most of us have to deal with, and you're probably not going to like tap into it and start sending open flow commands to it. But what you can do is tunnel over the top of it. And the same is true with any brownfield deployment. You can build these overlays wherever you want because the underlay is already there and already passes packets. Right? Potentially, this is also a way to look at the return to end-to-end. So remember those middle boxing from like one of the first slides? They're kind of maybe not needed. If you're pushing these functions out into this fabric, right, you potentially can do policy and firewalling and all that stuff actually out at the ends, at the edges, which has some potential benefits. You can kind of build these service chains and service fabrics, service meshes to really kind of push all the control out to the edge as far as possible. I don't know if that's 100% true, but kind of, right? In summary, we're a little bit hot here. I think one thing to back up a little bit is the map is not the terrain, right? So this is definitely a model. It's not necessarily something that's going to be a concrete reality today for everyone, but I think it is a tool that you can use to think about networks in maybe a slightly different way and come up with some pretty cool architectures and interesting ways to do this. So in summary, I think overlays are normal. You're probably already using them. Models are helpful. You're definitely already using some of those. It's a digital world, and I think software is king, right? So especially if we want to talk about scale and agility, the more we can put in software versus hardware, the better off we're going to be. So use the two. Core underlay to move bits, and an access overlay to provide services.